Hello, everyone, and welcome to our EDCON Hack workshop, which is brought to you by LinkTime and CryptoChicks. Today, we're going to talk about building your first state channel. This workshop will be delivered to you by our mentor, Trevor Clarke, VP of Product at Amber Data. In this workshop, we're going to learn how to build your first state channel, and we are going in the beginning, go through theoretical material, and after that, we are going to come back to it and actually do some practical stuff. So as I mentioned, the workshop brought to you by CryptoChicks. Please don't forget to register at our website at con.io/hackathon, and follow us on social media channels. As usual, we will be posting our social media contacts at our website, and I also will post it in the chat. At this point, I would like to turn it over to our mentor, Trevor, who will start with the workshop. Trevor?
Hello. First off, I'd like to thank everyone for joining us today. I'm really excited to share what we have with state channels, and hope that you take away a few hints and tips and tricks for how to build your own state channels. So I'm going to share my screen and we'll get started. All right, so building your first state channel. Today I'm hoping to cover the basics. This is all of the things that I've been learning, and I'd like to share with you some tips and tricks as well. But first, I'm Trevor Clarke, like she said. I'm actually a passionate blockchain engineer, and I've been doing this for about 2 years now. And I like to hobby with 3D printing on the side. Just a little bit of housekeeping before we get started. The discussion today will be first and foremost on the background and some setup for state channels. And then we'll dive into the code. We'll look at how you can actually implement a state channel in Solidity. And then at the end, we'll go through questions. So as you see me talking about different topics today, please do put those in the chat, and then I will go through those questions at the end of the conversation today. Without further ado, let's jump into it. So state channels. First and foremost, they're the scaling solution where 2 or more participants can transact information in a trustless manner without forcing the transaction to be submitted to a blockchain between each state change. So there's 3 key pieces that a state channel is composed of. First and foremost, it's a multi-sig wallet. What I mean by that is there are one or many participants in a contract. Secondly, they are an inter-party state communication. So that actually means I can transfer data outside of a blockchain, and that is communicated with all participants in that contract. So if I'm participating in that contract, I should be able to hear and see all of the state changes that happen. And lastly, it is a state finality mechanism. So as we make changes to the state at the end, there is a way for me to validate that that state is correct and store it back to the blockchain. That also can have a dispute mechanism so that we make sure that the mutations to the state are valid and true and trusted by the participants in that state channel. So a few things that are interesting here. The pros for a state channel, the reasons why you would want to use them in your project. First and foremost, checking that state is free. So when I'm sharing the messages, usually it's a peer-to-peer connection, and I can get the state very quickly. Secondly, it supports 1 to the n degree of transactions throughput. So as long as they are valid, the sky is the limit with scalability. That scalability is then put onto your technology stack. So if you're running a server, the throughput maximum of that server is now the scaling factor rather than the scale of the blockchain. Lastly, it's really good at instantaneous payments or data transfer. A lot of people are using state channels for things like delivering video content or different media downloading data, essentially. There's a few cons here. The first one is it's still experimental. So a lot of researchers are looking into state channels, the different use cases, how we can best utilize this technology and keep it trustless. It also can get very complicated. State channels, from what I've seen, there's really good examples for how to use this in gaming or if you're doing a payment channel. But as you start to implement those things, the logic gets pretty complex. So just keep that in mind when you're building your own state channel. A few things here on the gotcha side of things. All of the transactions that we're sending inside of a state channel must be valid, as in I should be able to submit them to a blockchain at some point, and they will still validate and be able to be stored within the blockchain. And lastly, just a word of advice here, do not use state channels to transfer large amounts of value, whether that's large ETH value or maybe a digital asset that's worth a lot of ETH or some other token asset there. Make sure that you're being careful when you're doing that. If we look at the use of different scaling technologies overall for Ethereum, primarily the Ethereum blockchain itself is really good for the store of value and for transactions and the immutability. The scaling solutions on top of that would be things like a sidechain, where I can actually add a bunch of transactions on the side, and maybe they have a historical ledger of value. But those are things that I should be able to store value and look back at those transaction histories. For state channels, it's more ephemeral. It's between peers. The end result is stored back in the blockchain, and I should be able to throw away that history without any issue, because I see the last final state of that state channel, and I can prove that that data mutated in a way that was valid. All right, so I want to go through a few of the flows here. We're first going to look overall, high level, and then we're going to dive deep into what it looks like to transfer data and the setup of a state channel. So what we're looking at here is the general flow. I've kind of watered it down into these 4 steps. So the first step is the channel setup, where we deploy a contract. Second is the commit and stake, where we send data to the contract and the participants stake the value that they want to add to the contract. Third is the reveal state, when we take that committed data and we reveal it to all participants, and we validate that that data and the mutations to the state are true. And lastly is the disputes. So if there are any mutations that are invalid or parties disagree, that's when we figure out if the dispute and the challenge should revert some of those changes or close the state to the initialization of the contract. And just a small note here, this is usually the case where we have data transfer between 2 or more parties. And the generic flow that I'm showing you here is so that we can support flexible rules. In the example, we could use this for gaming. So this is another example that a lot of people are familiar with. The payment channels are actually what I would consider where state channels came from. So in this case, there's a couple differences. First, you have the channel setup, which is deploying the contract. The second setup here is a little bit different. So this is when we commit our balance change and we fund it with the actual balance change that we are committing to. Third is the validation of that balance. That's when we reveal to the other participant or participants the balance change that we're trying to accomplish. And then last, again, the dispute and resolution of that mutated state. Payment channels are usually between 2 parties, but there are other cases where it is many to many. So now let's look a little bit deeper into that generic state channel that I was talking about at the beginning. So if we look at the beginning here, I'm going to use Alice and Bob, which I'm sure everyone's familiar with in the blockchain space. So I'll zoom in a little bit here. In the channel setup, Alice is the one deploying a contract. She's the one that's going to deploy it with some level of stake so that she is committing, this is where I want everyone to use the same level of stake, whether it's 1 way or 100 Ether. I would highly suggest using a small value, but the value that will accurately represent the data that is being distributed in the state channel. So the second part of that is she will broadcast the setup phase. This is telling everyone else, hey, my state channel is ready. Please join if you are interested. One of the use cases here is I could deploy a voting contract, and that ballot could be joined by many people ready to vote and mutate the state for their tallies in that ballot. So the second part here is the committing and staking. This is when Bob wants to join into this multi-sig state channel. So he now is the second participant. The first thing he's going to do is submit a transaction with an equal value to the stake that Alice submitted. That in turn has equal staking and equal value that both parties agreed upon. So now they have somewhat of a trust with that value that they've attributed. Second is he's going to submit a hashed data of what he would like to mutate on the state. So this is something that it's a one-way hash function that will store that data in a way that Alice can't necessarily see the mutated change, but she knows that she can validate in the future. And last, he's going to broadcast the commit status, which allows all the participants in this state channel to recognize that we're ready to start mutating and validating that state data. So now we move over and the channel is open. This is when Alice can commit a data change or a mutation to this state. I will be going through another data example with this in a minute. So we're going to go a little bit quicker through these next steps. So Alice sends some more data, then Bob can validate that data that Alice has sent. He can go ahead and reveal the salt for his data that he previously sent as a hashed data and commit that into the mutated state there. And this is actually where the state channels become a scaling solution. This is the magic of a state channel. You can actually come up with rules however you would like to for the changes and updates and validation to your state. And this can effectively loop as many times as you need to. You can have participants take turns, or you can have participants push different data at the same time. As long as everyone participating gets the update and is able to validate that state change, that is when the state channel is working correctly. Lastly, the channel will begin to close when Bob signals the reveal phase. This is when you take all of that hash data and you say, here's my salt. Here is the one piece of data you didn't have, so that you can actually validate in a one-way direction that the data I submitted when I staked over here is valid and that mutation is ready to take place. So that's when we go into the reveal phase. This is where Alice says, okay, Bob, sounds like you want to show me your data. I'm going to validate with your salt and with your input data and double check that what you pre-committed is valid. And if it is, I'm going to store it on the blockchain. And that's going back to the main Ethereum blockchain itself. If it's valid and if the data matches the original input. Now, if there were any issues, if Alice sees that Bob had changed the data in some way, or if Alice had changed the data in some way, Bob could submit a challenge, and they can go into the dispute and validation phase. So there's a couple interesting things that you can do there. One is having expiration. Maybe they get disconnected from the peer connection, or maybe they don't actually want to continue with updating the state. That's when the stake remittance and the last known state could get back to the main chain, and we close out the channel there. So let's go to the last example here. So I want to show you exactly what the data itself looks like now that we've talked through that. So we'll go through this one more time, and I hope that this will be 100% clear now. So for the channel setup, when we deploy a contract, we're also going to assign a value of Ether. This is an example of 10 Wei. So we think that the data is worth about 10 Wei. If we lost that stake amount, we wouldn't be too hurt by it, but it's still enough to say, I want to trust this data. So the second part here is when Bob says, okay, I will match your value and I will add my hashed data. So in this case, we have the hashing function I was talking about. This could be something like the catch-ack function, or maybe you're doing elliptic curve or something. You're submitting data and you're adding a special key that you only know temporarily and you reveal in the future. So this isn't something like your private key that you want to use. This is just a random string or number or something to make that hash be different than something that could be guessable. So once Bob commits that to the state, then the channel is open. And now Alice can submit her data. In this case, I'm only going to loop through once just to show you how that data is revealed. So she submits data A, and this is just data that is in its final state. She's not hashing that data in a way that she would need to reveal in the future. So you could actually play with some of the rules in how everyone is submitting their data here. But for the case of this example, it's just raw data. But she doesn't have a way of knowing the hashed message that Bob sent initially. So now Bob is going to validate that, and there's not much to validate because the hash is not wrapping Alice's data. But since everything's valid, he goes ahead and signs the next commit of data that he wants to change with the state. In this case, everything that is submitted into the state channel is valid in a way that he's happy with. And so he adds the salt. This is the random string or whatever password that was part of the hash function variables. So this allows Alice to check that the original data was sent correctly and that it matches what was pre-committed. So once Bob adds that, he sends it to Alice, and now he can signal the reveal. So at this point, he can submit the status of reveal. Now, all the participants will get signaled of this status change, and they should be able to validate all of the original data. So when signaling, Bob has added the input data, he's added the salt, and he's added the hash function. So every piece of data there can be verified. So Alice goes ahead and uses the salt and the original input data and puts that into the hash function and validates that it's working. Now she commits that the status is revealed and the state can then be updated on the chain. So I want to do a quick example of what it looks like to do a dispute. In this case, there's one change here. So if we look back at the validate and reveal section, the message that Alice committed was data A. In this submit challenge, Bob sees that either someone has tampered with the data or Alice actually shifted to data C. We don't know where that came from, but it doesn't match the original. So Bob sets the status to dispute and opens a challenge to use the contract to validate that data. So this is when the contract will say if it's valid or not. And if it isn't, it can revert the state, or it can do a couple other functions for expiration or stake remittance at this point. Now, I'm not going to talk about disputes a whole lot today in our demo. I think that would take a lot of time, but there are actually resources that I linked to at the end that you can actually dive deep into how to do dispute management, how to do lots of different validation rules, and how to do some of the expiration flows and stake remittance. So this is when I consider the channel closed. All right, so that's all I have for the introduction of state channels. Now we're going to take a little bit of a different approach here. We're going to change into Solidity and implement the bare bones of what a state channel needs. If you remember, it's those three things where we have a multi-sig wallet, which is 2 or more participants. We're going to implement the different rules that it takes to transition the channel status and the validation of the state changes. So this is what we're going to do. We're going to jump into Atom and start looking at how to build this channel. So the first thing we want to do is add the status. So if we look back in our documentation here, this is the flow that we want to enforce with our state channel. So I'm going to simply create an enumerable. We're going to call this channel status. So inside of here, we have those 4 states. So the first one is the setup phase. The second one is the commit phase. Third one is reveal. And lastly is dispute. So this is going to be our control flow, if you will. Now, we need a few variables to keep track of over the course of this state channel. However, I'm going to do this at the top level. This is something that you could abstract into maybe a struct or something later and use multiple channel setups from one contract if you would like to. So first and foremost, I'm going to set up a stake amount. So this will keep track of what was originally submitted so that every future participant matches that stake amount. Second, I'm going to set up the current status, which will be public. Both of these are public actually, so we'll do that. Current status is going to keep track of the channel status. Next, I want to know all of the participants, and I want to keep track of all the participants. So we're going to do an array of addresses, and this is going to be public as well. So we'll call this participants. And then lastly, I want to keep track of the hash data that is getting submitted from the different participants. So here I'm going to create a mapping, and we're going to pass in the address, and we want to hash into something that is like a string. So we're going to use bytes 32. And I'm just going to call this hash data list. So now I think we've got all of our variables. Now it's time to walk through that first step. So when Alice deploys the contract, she's going to submit a little bit of ether value, and that's going to be stored as the stake. So the first thing I want to do is require that we have at least some kind of value in place. So we're going to do message.value. And that has to be greater than, let's say, 1 way. We're going to give it a nice little message that says stake is required. The next thing I want to do is store that stake amount from the message value that was passed in. So I'm going to do stake amount equals message value. And I also want to keep track of Alice being a part of that participant list. So we're going to do participants, and we're going to pass in Alice, which is our message.sender. So if you're familiar with Solidity, there are globals that happen with each transaction. So message and block and some of the other ones are all part of the documentation if you're curious. But these are very standard variables that I don't have to define or pass into from the constructor. And the last thing I want to do in the constructor is set the current status. So if you remember in the documentation, when I do channel setup, 2 things that are required are 1, pass in the amount of value I want to stake and I want others to stake. And then second, signal that the setup is complete. So here we're going to set current status to, we're going to do uint8 conversion for that enumerable and do channel status dot setup. So at this point, we should be able to cover the first channel setup phase that we chatted about earlier. The next thing I want to talk about is the actual data. So the second part was the commit and stake, and Bob is sending data in a pre-commit fashion. So let's walk through what it looks like to do a simple hashed value and allow Bob to use that hash value from the contract before he submits that to the contract. So I'm going to do a new function, and I'm going to call this get hashed value. And this is where I'm going to send in a few parameters. The first one's going to be a value, and it's going to be just a standard integer. You can put whatever you want here. This is the data itself in that value. The second I want to keep track of is the salt. So I'm gonna assign a salt when I pass in this method. And lastly, we want to know who is sending this. This is something that we could check. Like, we want to reuse this function multiple times, so it's not always going to be a message.sender type of function. So now we need to reveal this as public, and it's not going to change state, so it's pure. We're going to return the hashed message that we talked about here, and that's a bytes 32. So we're going to do a bytes 32, and we'll just call this message. Okay, at this point, we have everything we need to submit. So what we want to do now is return the hash function, and that hash function will return the hashed data that we want. So we're going to do a catchact function, and we want catchact 256. That's a standard function from Solidity. Another one that I'm going to use is abi.encode packed. So that's going to take our values that we send in and organize them in a smaller package. We're going to pass in our variables here, so value, salt, and sender. And that's just going to give us a one-way hashed value. So at this point, I should be able to calculate the pre-commit data. The second thing I want to do is check if that hash data is correct. So I'm going to copy this function and change it slightly. So instead of being get hashed value, I'm going to say is hashed value correct. I actually want to change that to be is hashed message valid. So again, we're going to send in pretty much the same variables here. The only difference being we need to compare it with the previous message. So we're going to add bytes 32 again, and we're going to call this hashed message. We still have everything else the same. The last thing we want to get is a Boolean value. So we're going to return a bool. Oops. So down here, we're actually going to use the function that we used above. So we're going to say this, and we're going to use the previous variables. And we want to compare that to the hashed message. So that way we can get the valid same comparison here. Now, these two functions are just for demo purposes. There are many different ways that you could implement this. In fact, it's important as you're building your own state channels. Build them in a way that makes sense for your application. So the next thing I want to do is create a few helper functions. This will allow us to validate the flow is working correctly. And at the end, I'm going to put this code into Remix so we can step through what the state channel is doing the whole way. So here I'm going to create a function, and we're going to call it is status setup. So this will be the first setup state. It's going to be public. It is checking state, so it's a view parameter here, and it's going to return a Boolean. So in here, we're going to return current status equals, and we're going to compare with our enumerable. So we want that uint8 and do channel status dot setup. So we're just going to do a couple of these really quick so that we can check for all of those enumerable values and the state. So we're going to check the commit state. And we're going to do the same thing for reveal. And lastly, dispute. Okay. So there's a couple more functions that we need to implement. At this point, we have everything we need for Bob to submit that hash data, but he doesn't have a way of submitting his stake. So we need to create a stake function that allows him to submit the same value that Alice predefined in our contract state here. So I'm going to create a function. This is going to be stake. Bob is going to submit his predefined data. So he's going to pass in his hashed message. And it's going to be an external function that anyone can call, but we're going to validate. It's also payable. So this is allowing us to send real Ether amounts. So a couple things we want to validate here. One, is Bob sending enough value? Is he not? If he's not sending any value, we want to not allow this to happen. Second, we want to make sure that that value is the same to the stake amount that Alice predefined. So we're going to write a couple require statements here. Message.value is greater than 1 way. And we're just going to say requires stake. Second, we're going to require message value to equal the stake amount. So we'll write a message stake must be equal to initial value. Okay, so we validated the input that is coming in. Now we want to add Bob as one of the participants. So we will add participants. We will add message.sender, which is Bob, into the array. Now, if you remember, I created a hash data list up above. This is going to keep track of the pre-committed data. So I'm going to add Bob, message.sender, as our first value here. And we're going to set that equal to the hashed message that we passed in. And the last thing that was part of that second phase, there were 3 values. One is the Ether stake amount. Second was the pre-commit message. And last was signaling for others that we are done with the commit phase and we're ready for that channel to open. So we're going to do that in a way that checks to make sure we aren't in any other state. But you can actually play with this part if you would like to in the rules of your state channel. So I'm going to check that current status does not equal reveal, because I don't want this to be in the reveal state when someone tries to stake. So we're going to do a uint8, and this will be channel status reveal. And I want to do that also for dispute. We don't want things to get ahead of us. If all of that is good, we want to use the commit phase and store that. So one thing that I want to point out here, so in phase one, we submit the contract. That's one transaction. So that will be the normal Ether fee that you pay. The second one is Bob committing his stake, and that's another transaction. And that's an actual Ether value that's getting transferred. Everything after this point is actually what I would consider free because you're participating in a peer-to-peer connection. So that's when you can scale however you need to and validate and execute rules for your state. At that point, once all of the state is mutated, then you close out the channel with your final transaction fee. So it actually keeps things really lightweight. And it can get even more lightweight if you're using the create2 method that came recently with the Constantinople fork. So there's one more function that I want to write for our demo here, and then we'll step through it, and then we'll talk through any questions that you have. So that is the reveal state. I don't have enough time to go through the disputes and other things. Like I said, we'll have links at the end for that. Let's dive into the reveal function. So here we want to double check that valid data is sent and that the final state is ready to be submitted to the blockchain. And lastly, send back any stake that wasn't really needed. So we're going to create a function called reveal. And here we're going to use a few parameters. The first one is going to be who we would like to revert the stake back to. This is likely going to be Alice, but we're going to make this address payable. And we're going to say claimer. The next one I need is the value, the amount, the data that we sent in. We need to pass that in and validate it. Make sure that it hasn't changed since the first commit. The next one I need is that salt. And then after that, I need the sender. So those are the same things that I passed in when I did the get hashed value above. Lastly, I need the original hashed message. So we'll do bytes 32. Awesome. And lastly, it's going to be an external function. Okay. Inside here, we want to double check that the values are still the same and we're validating that the data originally hashed is still valid. So that way we can submit the final state. I'm just going to do a very simplified version of this so that you can see what that looks like. But this is where things get really complicated. There's many different ways of accomplishing tasks in state channels. So we want to check if it's valid. I'm going to store this as a Boolean, and we're going to reuse the method is hash message valid. So this is when we, again, use the value salt sender and our comparison hash message. We're going to require that this valid Boolean equals true, and we're going to signal final state is invalid if it's not true. This is a pattern that I've seen many other state channels do. In the reveal phase, to close out a state channel, a lot of times they do self-destruct and pass in whoever is going to get the remaining stake. But again, this is pending whatever use case you're trying to accomplish. Okay, so I think at this point we have everything we need. I'm going to transition into Remix and let's see if we can validate that this is working correctly. So I'm using solc 0.5.0. We're just going to see if everything's good. Looks like I might have a typo somewhere, so let's see what that is. Yeah, That was definitely a typo there. And let's see, declared as pure. This one is reading from state potentially, so we need to change it to be external view. Awesome. I think that clears up all of our issues. Now let's go ahead and run our contract. So going back to the beginning of that phase, just to reiterate, we wanted to use JavaScript VM. So it'll preload me with 100 Ether. Let's pretend that CA3 is Alice. And we're going to submit 10 GUI. We're going to set that to be our stake in our initialization of the contract. So if we set 0, it should actually not allow us to deploy. So if we look down at the bottom here, there was a revert. So let's go ahead and set that as 10 GUI and deploy. Great. So now we actually have all of the functionality. Let's go ahead and check if the status is set up. Returns true. Is it reveal? False. Okay, great. We also want to double check that Alice is part of this. So check the first position of the participants array. CA3, CA3. So that's Alice. Cool. And we're double checking that the stake amount was set correctly. Looks like it is. So at this point, we've confirmed everything that Alice has done is valid and correct, and the deployment is great. So we're going to move into Bob. We're going to shift from CA3 to 147. At this point, we want to generate the data that he's going to send to the contract for the pre-commit. So we're going to go in here and do get hashed value. I'm just going to create a random character string here. Do that. The salt we'll do is 1, 2, 3. Anyone could guess it, but it is what it is. We're also going to copy the address we need and hit call. So that gave us the bytes32 message. Now we have all the data we need for Bob to start his part of this state channel. So at this point, we're gonna call the function stake, and we're gonna pass in that that message, that hashed message. There will be something that happens here. So we didn't pass any stake, which is good. We validated that we needed that stake in the transaction. So we're gonna hit that again. And it looks like it was successful. So now I want to double check, are there 2 participants? 147 and 147. So Bob is now a part of this state channel. And he should have changed it to be the commit phase. So commit is true, and now setup is false. So now we've changed our state machine to be a different phase of this state channel. So this is when we can start a peer-to-peer connection. Some people do that with WebSockets or maybe other mechanisms. That's when the state can transition and mutate however needed. But every time we need to be able to validate that that data change is still okay. So what I'm going to do now is pretend like the state is done mutating, and Bob is going to signal that reveal is ready to go. So he's going to send in that hashed message. He's the 147, and hashed message is that. The salt was 1, 2, 3, and we're gonna falsely put in some values here, and it's going to hopefully not work. Awesome. So we got to revert. Final state is invalid. We want to remove the 3 here. Now this should work. Great. So when I did the reveal, if you remember down here, it actually hit the self-destruct function and changed that stake to send to Bob. At this point, you could do all the rules for the dispute. You could have expiration or different ways of passing the staked values back to the participants. But I'll leave that up to you. So if we check anything else, if we look at the status, it's going to error out because we've self-destructed the contract. All right, so I think we've actually covered just about everything for the state channel. At this time, you could actually take this and deploy it with Truffle, and you could put that into Rinkeby. This is when you can start your local development, and I would highly suggest testing it out with a peer-to-peer connection where you're sending that hash data back and forth with the flow that we walked through. So everyone participating, I'm hoping you've learned a lot and that you will be able to use this in the upcoming hackathon. When you do, I'd like to announce something very special. We've actually recently launched our Amber Data IO APIs. So these are full validated blockchain data that you can use while you're creating your projects for the EDCON hackathon. We also have market data and really awesome WebSockets for a lot of different use cases. So I highly encourage you to check that out. So I will be allowing you to see that link. If you go to statechannels.netlify.com, everything is linked there as well. If you go to docs.amberdata.io, you can see the APIs as well, and they're free to use. So at this point, please take a look at the references that I have here. A few that I want to point out, the research that I've been doing with state channels, a lot of inspiration was pulled from the Force Move games by the Magmo team, Counterfactual, and then some older implementations, toy state channels and simple payment channels from IPFS. I highly encourage that you read through some of those, and the Force Move games white paper is also really good. The rest of these are excellent resources for you as you develop your dApps. So that's all I have for my presentation today. The code is linked here in the state channel demo. It's on my GitLab repo. So feel free to fork that and make use of that as you will. The only note there is it's not ready for production. So take that with a grain of salt. All right, so at this point, I'd like to answer any questions. I'm just looking in the Zoom group chat. If you would like to submit a question at this time, I can answer it to the best of my ability. And we can go through that if you would like to.
Hello, everyone. While you are thinking about your questions, I would like to talk to you about our next workshop. Our next workshop is on Ethereum 2.0 Phase 0. It will be delivered by our mentor, Justin Drake, Ethereum researcher, and he will discuss the Ethereum 2.0 Phase 0 details of specification. As another reminder, please note that EDCON Hack is open for registration. You can register at the website, which is shown on the screen. And don't forget to follow us on the social media to get the information about the upcoming workshops. And now, back to Trevor.
All right, thank you. It looks like we don't have any questions, but I am available on Twitter. So if you look at twitter.com/TrevorJTClarke, I will answer any questions you have in the future. And you can also reach out on the GitLab repo, send issues if you want to, and I can discuss those with you there as well. Thanks, everybody.
Thank you so much, Trevor. It was a great presentation. I definitely learned a lot, and I hope everyone else on the call learned a lot as well. As a reminder, this workshop will be available in the recording on our website and YouTube channel. So please, if you need to do any reviews or share it with your hacker friends, please feel free. Thank you very much, and I'm looking forward to seeing you at our next workshop. Bye for now.